lectures. There are 2 more lectures left. So hopefully it's a quick day. Okay. So the first let me share my screen. Can you see my screen?
Yeah, it's a.
Okay. Yeah. So the future trends in sustainable ammonia production. And again, so we all know yesterday we spent a lot of time talking about the hydrogen production from the natural gas. So the green hydrogen is from the renewable power. So there's another way to produce hydrogen, which is clean hydrogen without emitting CO2. Okay, so essentially anything related to ammonia production, you cannot separate from hydrogen. Is ammonia is from the so-called either green power or from the clean hydrogen. So that's what we have discussed yesterday. Today, I want to just highlight some trends, that I observe, in the future ammonia synthesis. So I think to summarize what we have discussed in the last 2 weeks, we have been talking about all different ways to make ammonia, electrochemical and microwave chemical looping and plasma, everything, right? Those are our approach. But once you make ammonia, what can you do? Immediately, you can use ammonia as a fertilizer. Remember, at one time I said the separation of ammonia. If you want to use ammonia as a fertilizer only, you can just put into the sulfuric acid and then to make a fertilizer. However, ammonia can be used for many other things. So it'd be good to make ammonia because ammonia is a hydrogen carrier, all right? So once you make ammonia, and then you can transport to another location and turn ammonia into hydrogen. So anyway, so first, let's talk about the ammonia fuel cell. Let me ask the audience a question. The hydrogen. Everyone knows hydrogen fuel cell, right? The theory of hydrogen fuel cell.
Yes, sir. Solid oxide please.
So you know you all know the PEM fuel cell and solid oxide fuel cell, all right? I don't have to. Yeah, I don't have to talk about theory. So you know that, correct?
Yes.
Okay. So what is the ammonia fuel cell? Okay. So ammonia fuel cell, there are 2 different. So this is the hydrogen fuel cell, all right? So PEM fuel cell means it's low temperature. Using hydrogen, and solid oxide fuel cell is high temperature. And you can use the H2 or the natural gas. Okay. So, but when you use natural gas, there's unknown reforming. Okay. So all this is the fuel cell. Now the same thing. Ammonia is also the oxygen carrier. All right. No, it's also energy carrier. As long as you have a fuel property, which is energy, that you can use as a fuel cell. So one way to use ammonia as a fuel cell can be used as a power fuel cell, where it's a direct oxidation to nitrogen, i.e. direct ammonia fuel cell, or by supplying hydrogen to the hydrogen fuel cell. So one way to use ammonia as a fuel cell is you can decompose ammonia. I think that I have one session already discussed about ammonia, the decomposition. You can decompose ammonia into hydrogen and nitrogen, and then you use then use hydrogen as as a fuel cell. All right. So today I'm going to talk about direct. What if you direct the burn of the ammonia without turning into the hydrogen? That's what people using. It's called ammonia fuel cell. So here's what. So ammonia fuel cell, you can use ammonia fuel cell without the without the converting it to the to hydrogen. So one way is basically the ammonia decomposition and hydrogen. Okay, this is the so-called indirect. But the direct fuel cell means you can turn ammonia into the NO and then the ammonia eventually to water. The whole process does not include the hydrogen production, but you still can run the fuel cell because there's the electron produced during the process. So that's the future trend in US. So people basically are saying that I don't have to go through this process. Let me circle this. What I circled is called the indirect method. So what I circled here is called the indirect method, and which you decompose the ammonia into hydrogen, nitrogen, and then the hydrogen feed into the fuel cell, let's say PAN fuel cell or solid oxide fuel cell directly. Okay, you can do that. So this method shown here is called so direct means without turning the hydrogen. Okay, so but it's more complex. You have to design the fuel cell and then following the oxidation step. It's all about the oxidize the ammonia into the nitrogen and water, and then to generate electricity. And here's the steps. And this is the very complex the process. First, ammonia is that so ammonia reacted with hydroxyl and then form the different ammonia species. At the end, ammonia turn into nitrogen and water. Okay, this is more like if the multi-step ammonia fuel cell, eventually this process is equivalent to so that's all. So basically, ammonia you have you carry the energy and then react with the oxygen. It's more like combustion in the form of nitrogen and water. So instead of going through the combustion and with O2, and then the ammonia actually undergoes the different step react with the hydroxyl group instead of O2, and eventually turn into N2. Each step you saw the electron coming out. Okay, when electron coming out, that means the energy is generating. Okay, make sense?
Okay.
Go ahead. Anybody has any questions?
No, sir.
Okay. So that's the how you design ammonia or ammonium fuel cell. So while we are speaking, there are a number of the companies or countries they are actually burn the ammonia, including Japan. But and burning ammonia is a lot of work. You have to introduce ammonia into the existing infrastructure. Existing infrastructure means either you introduce ammonia in the cold combustion, or you introduce ammonia into the natural gas combustion. Okay, so that's the this reaction combustion. Two, the whole process doesn't generate CO2. That's the objective, because you begin with so-called non-carbon fuel, react and then produce the energy. Okay, so the complexity of this, you have to go through this process in order to generate energy. So I'm going to the pause here and let's analyze the. I mean, okay, we do not do combustion. We go through this the process. Let's list a couple for the based on this the steps. I want the audience to tell me what's this advantage and disadvantage. So this is the exercise we need. So just a couple bullet points. What's the item? You're right. Okay. Advantage of direct the ammonia fuel cell and disadvantage of the direct ammonia. So what's the advantage of this? Anybody can just
no need, no need of hydrogen, sir.
Thank you.
So, hydrogen storage is difficult, but ammonia storage is easy.
So no need to decompose all right. So no need to use decomposition. Remember there's one section, I think on the day 4 or day 3, we are talking about ammonia decomposition. What's the challenge of ammonia decomposition, if you recall? The challenge of ammonia decomposition, it is 100%. You can decompose ammonia easily, but it's 100% decomposition at low temperature. All right. So you have the decompose ammonia decomposition. Do you remember? Is it endothermic or exothermic?
Endothermic.
Endothermic, yes. Because the ammonia synthesis is exothermic, all right? So, and then the reverse reaction is endothermic. That means that reaction requires heat. That means the high temperature will favor ammonia decomposition. So but if you go to too high temperature and then you waste energy, all right? So the challenge is, what if we operate how low the temperature we can operate to achieve 100% conversion, which is a challenge. Okay, so now no need to use catalyst for the decomposition, which is good, because to decompose the ammonia, the 100%, and then you have to what you call that? You have to use the catalyst operate low temperature. There are a lot of challenges. Okay, so let's see the. Okay, so the advantage of DI, you don't have to, no need to catalyst, no need to do the decomposition. Okay, so anything else? Advantage?
Easy transport.
Yes. So it's the fuel cell. Yeah. Keep in mind that we are talking about ammonia fuel cell. Fuel is ammonia, is a liquid. Easy to transport. All right. So imagine if you use the hydrogen, doesn't matter you decompose or not, you have to have some kind of infrastructure to transfer the hydrogen. So this fuel is liquid, easy to transport, and easy to feed into fuel cell. Okay, so there are a lot of advantage. Okay, all right. So let's stop here and then go to this one. Now from this class, you probably learn anything there's an advantage, there must be disadvantage. All right, so nothing perfect. So what's the disadvantage of the ammonia fuel cell? I think at one time I mentioned about the remember we are talking about a different way to make ammonia, the very high level. So then we talk about the ammonia, and then I asked the audience question: when you use the ammonia in a laboratory, so what kind of regulator you use something? Anyway, I want to give you a hint. So let's start. So what's the disadvantage of ammonia?
Ammonia is basic nature. It is not neutral.
Non-neutral. Okay, good. So what else?
Then its odor is pungent. It has strong pungent smell. Bad.
A smell. Is that what you're saying?
Yes.
Oh, okay. So that's called, okay.
Bad odor.
Toxicity. All right. Toxic. All right. Is that what you're saying? Toxicity. Toxic. Is that right? Is that what you're saying? It smells. All right. Corrosive. You agree? Corrosive means certain part of the ammonia fuel cell you cannot use copper. Follow me? Copper.
Yes,
or what I would say, yeah. So I think I remember during the time I asked you, hey, if you work in laboratory, what kind of I'm gonna put in here.
Regarding the conversion efficiency.
Yeah. So yeah, go ahead. Right. So remember, okay, go. Let me stop. I will stop writing. Just go ahead. What? Say it again. What's the disadvantage?
Conversion efficiency. We are losing hydrogen, sir. If you directly use hydrogen in fuel cell, then the efficiency is different. In ammonia.
Very good. Thank you. Thank you. Very good. All right. So, yeah, low efficiency due to low concentration. That's right. Because you have to, if you use a pure hydrogen, low efficiency, lower, I would say, lower efficiency, and due to the low concentration, because you have to, when you use it, you have to decompose into N2 plus H2, and then the majority is nitrogen. You're right. Basically, you are dealing with dealing with a diluted.
Yeah, only 70% is hydrogen. Remaining things are 70%. Yeah.
Yes, very good. Yeah. So basically, you use hydrogen pure, you subject to the disadvantage of hydrogen because transportation, and but at least the pure hydrogen you have the, let's say, the high efficiency because you feel it's high. Now use ammonia and then you have to decompose, and then when you decompose, you're dealing with the diluted, okay, diluted hydrogen. Very good. Yep. So We talk about. I think I'm talking about corrosive. Here's the something the I want to show you. This is regulator, pressure regulator on the cylinder. It should be so. If you I don't know what's the coding in India about the using of the gas cylinder. So for the ammonia, you have to use the stainless steel. Most of the gas you just use the brass, or people say copper or the brass regulator, but for ammonia you have to use stainless steel regulator. the the connector on the gas cylinder, and then you can tell brass will not connect, so you have to buy. It's very expensive. Stainless steel, the regulator is very expensive. So that translates to the parts of ammonia fuel cell. When you make ammonia fuel cell, everything inside the metals, either stainless steel or has to be resistive to the corrosion. Otherwise, that fuel cell will fall in apart. Okay, so that's the ammonia. So anybody want to add anything else on the ammonia? Okay. So if we know, let's continue the next part. So I'm shifting the gear. So because the future trend, another future trend is the plasma catalysis. Um, we uh, we talk about the plasma catalysis, and here's a quick summary of the plasma. So plasma can be generated via the different approach. One is let me list it since we are talking about plasma. So this is a quick summary of the plasma the chemistry. So you can use the microwave to generate plasma. Okay, that's the DBD. Plasma. So there's another way to generate plasma is so-called DBD. That's called plasma. So the corona discharge. Corona discharge the plasma. So no matter what you do, and then here's the way normally the plasma you basically you turn nitrogen into the different species, active species, and these active species either they combine to form ammonia or they basically decompose to form the nitrogen. So you can use the plasma to decompose ammonia as well, and or you can use the plasma to generate to synthesize the ammonia. So either way is going to work. But key is you have to let me draw the key is you have to generate the key is you have to generate a species. Okay, so active species. Remember the activation energy we are talking about. You once you elevate the species, it becomes very easier. Okay, so I want to maybe I can draw we'll come back to this one. Okay, so ammonia you can do either synthesize ammonia. This is something I really don't want to go to annotation because every time I use this function, every time I use this function, my computer stops. Hold on, I'm going to share it back again. but I do want to draw something. Okay, here we go. So basically the forward direction and the reverse direction, you can use a plasma as well. So you start from one state and you cross the activation energy, and then you release heat. Okay, so this is N2 and the H2. So basically, this way you make ammonia. Okay. So keep in mind that you have the this is the activation energy. You have to cross the energy barrier and then going to this side. So with the plasma, you actually build up in here. You start from here. It's basically N2 star. All right. So everything. So you cross mountain and then you go this way. Now, if you have the ammonia decomposition, you can do the same thing. So you can basically elevate the NH3 into the species H2 star, and then you can go this way. Otherwise, you are facing endothermic reaction. In order to reach 100% conversion, and then you have to input a lot of energy. So I introduced microwave decomposition, the reaction where you can achieve the 100% the conversion. So there's different way to activate the species. If you want to make ammonia, you can activate the nitrogen reactant, and if you want to activate do the decomposition, you have to put a plasma on ammonia so that they can cross it and then turn into 100% conversion at a low temperature. So anyway, so I cite this from a paper, and then this is what I show you. So the key is there's the decomposition and then the species recombination. So that's the challenge of the ammonia decomposition, because the reason you cannot reach 100% conversion is if you look at this the cartoon, they actually show you there's a decomposition, but there's a recombination that's kind of against you. Okay. Anybody has any question until this point?
No.
Okay. So yeah. So this way to basically to make this is the trend in the ammonia synthesis. It's not just how you make ammonia. Once you make ammonia, you solve the transportation issue. That means this hydrogen made into ammonia can be transported to the end user. But end user receive ammonia, and then what can they do? They can directly use ammonia, and then for hydrogen generation, decomposition. If you remember, we talk about a lot of method of ammonia decomposition, and but now this relationship shows you ammonia decomposition can be turned into the plasma. Okay, so that's to solve the challenge. Yeah, I don't want to go back to give you a review, but if you remember in the decomposition reaction, the challenge of ammonia decomposition is 100% decomposition at a low temperature. That's the major challenge we have discussed last week. Okay. Anyone has any question at this point about this? The basically relationship of ammonia. Okay, I'm going to ask you the question. I think I remember. I don't know if you still remember the audience. I want to ask you the question, and then basically you are talking about efficiency of the plasma. Okay, so let me make a point. It's very important how I remember we are talking about how you generate nitrogen plasma under pressure. So most of the time, you you use argon. So let me I'm stop talking. I'm gonna stop sharing and then share my screen again. So this it's very important. I think that I'm gonna tell you the real world experience on how you operate a plasma. So we are here, all right? So I'm gonna add the one one slide. What I'm doing here? My so for the audience, if you're working using microwave or any the DBD in your laboratory, just let me know, okay? So I'm talking about microwave, how you generate plasma. Then I'm going to ask you a question. So basically essentially you have argon. Follow in, and then oh gosh, it's very easy to talk in a classroom, but okay. So you use argon and argon plasma, and then you introduce the N2, all right? So then N2 react with the argon plasma, then you form the inside here. So once introduced, and then you form the N2 star. Okay, that's how you generate plasma. Otherwise, you have to put a vacuum in there. Okay, here's my question. Okay, so just watch my question. Think about this. If you have 100, let's say this vessel, you have 100 N2 molecules in its chamber. You have 100 N2 molecules in the chamber. You ionize, let's say the 20. But your objective is to ionize all of them, all right? The remaining, this I'm asking question related to efficiency. I will tell the answer, okay? The remaining 80. N2. For the remaining, this is really talk about. So for the remaining 80 N2 molecules, how do you ionize them?
We have to recirculate through high pressure.
Yeah. So yeah. Okay. Good. Thank you. So yes. So you supply hydrogen, all right? Supply hydrogen species, hydrogen, and then which turn into plasma, all right? Is that what you're saying? So basically, I'm sorry, every time I try to type, my cursor disappeared. So that's why it makes me so difficult. Okay. So you supply hydrogen, which are turned, sorry, I'm going to slow down, which are turned into plasma. All right.
Yes, sir.
So, and then yeah, then what? Then this is the plasma will, which will ionize N2, correct?
Yes, sir.
Cool. Thank you. All right. This is the point I try to make. So if you have the 100 N2 in the system, you only need to ionize handful of the species. Then the other species, let's say they're shown here. If you look at my cursor, other species in here is going to continue ionize those neutral molecule. Okay, so to say differently, you do not need to supply energy to ionize all 102. I want you to remember, because while we're working in the plasma field, every time you go to conference, people challenge you saying that, oh, plasma is inefficient and then it costs so much energy. No, that's wrong. It all depends on how you operate. So I'm going to draw a conclusion. If you have 100 N2, okay, molecule, you do not need to supply energy to ionize all of them. Because other ionized species I don't know what happened with my cursor. Every time I'm typing, it disappeared. So because other ionized species will do the work. Okay, make sense? So if you do the energy calculation, so which means I will tell you to ionize N2, it takes 15.4 EV. Okay, so if you try to ionize the N2 to ionize the N2 molecule, you take this. If you multiply this by 100, then you say, oh my gosh, so much energy. That's the people do the calculation, and then in a conference or any publication world, you have the reviewer and everybody asks you the same question because they do not understand how the ionization has been taking place. The reason being that you just need to look at the species in this circle. Sorry. So you have to look at the species. I'm going to color code this. Okay. So anything in this circle, and then once it ionized, they will basically interact with the neutral molecule, and the neutral molecule will get ionized. It's more like nuclear reaction. It's a chain reaction. Nuclear reaction is at atomic. You have a neutron and heat. The atom. But here is the same thing. But at the molecular level, you have this activate, and then the active species or ionized, they are going to heat nitrogen. So it's very efficient. The conclusion is very efficient, but provided you have to do it correctly. The right design, you are not going to waste the plasma, because if you let the plasma neutralize, then with the reactor wall or with something, you waste plasma. You have to make sure in the chamber, all these species, they interact each other, so they are going to ionize the remaining neutral molecule. So to say different way, if you have let's say 100 ammonia molecule in the chamber, you only need ionize a handful of them. Let's say maybe 10%, 20%. Then remaining will be ionized throughout the process. That's the way to increase the efficiency of the plasma. Make sense? And any questions? Or you may have some experience in the laboratory. Okay. So this is the advantage of the so-called the plasma, especially microwave plasma. DBD is a little different. DBD is like they also ionize the species, but the DBD, the electron is super hot, but the remaining the body, the so-called ionic portion, molecular portion, is cold. But microwave is different. You have hot electron, you have a
audio live data.
hold on, okay. Yeah, I used to teach the ammonia safety. So I'm sure if you work in the chemistry or chemical engineering lab, you have ammonia, you see ammonia in the laboratory, all right? So typically, ammonia safety is more like this. If you can buy the 37% weight percent of the ammonia solution, okay? So if that's a laboratory, you can see those glass bottle, and then you have the ammonia concentration 37%, and then you be careful if you open it, and then the ammonia come out, you may have tears, because it's so irritating, all right? And ammonia is toxic, all right? So now I'm asking question: what if you have 100%? Anyone can guess what's going on if you have 100% ammonia tank leaks? You always have alarm. So ammonia.
So
anybody?
Is available, sir, for detecting that. If
Say it again.
Sensor is available for detecting the leak. If leak ppm is more than 1000, then that is toxic to human. So it will give an alarm. We can set the limit based on our based on the room space and ventilation. We can set the limit on the sensor. So if the limit is beyond that, then the alarm will shout automatically. So that we can rush up and we can take that as an emergency.
So basically you run away. You should. So ammonia at high concentration, if you breathe in if just assume you are not, so let's say you work in the lab, all of a sudden next to you an ammonia leak, if you breathe in accidentally, it shut down.
Yeah.
It shut down your breathing system. So they basically choke you, breathing system. So that means you die right away. So
yes.
it's very dangerous. Okay, so I used to teach in chemical plant and refine, especially what you call that petroleum refining. You see ammonia because there's a combustion for NOx reduction use ammonia. You will see a lot of the NOx the control the system, and actually there's an ammonia tank in there. They will be isolated and then stay outside. But sometimes in a laboratory, you do have ammonia tank. In my laboratory, I never store 100% ammonia because if accidentally breathe in, it shut down your breathing. You cannot breathe. Okay, so this is this is ammonia. So also, I mean, since we talk about ammonia safety, the two molecule I always mention in my class. Okay.
Yeah.
So the other one is called H2S. Okay, hydrogen sulfide.
Yes.
Hydrogen sulfide is opposite to ammonia. Because you can smell at what do you call that? Maybe ppm level. Okay, so ammonia is something. Ammonia is something. The moment you smell ammonia, you breathe in accidentally at a certain concentration, it shut down the breathing system. You die right away. H2S is dangerous a different way. You can smell. I'm sorry, I apologize for my spelling because every time I'm in a rush, you can smell at the ppm level. Let's say in a confined place and run away. Why? By the time you do not smell H2S, it is too late. You understand what I'm saying now, right? So it's different from ammonia. Ammonia, you smell, shut down the breathing system. Hydrogen sulfide slowly basically numb the sinus in here. And if you smell it, which is good, that means what you call that, your sensor in your nose still working. By the time they basically numb your sensor, it's not because there's no H2S around you, because it's too much. As you numb your sensor, your nose, and you die. Okay, so I mean, since we talk about this, I wanted to in the chemical plant or the refining, or you have ammonia, hydrogen sulfide everywhere. Okay, so because ammonia is for the so-called NOx control. You know, if you look at the stacks, you know, whatever exhausting the stack, there's always a tank. I think it's yellow colored tank, the next to it. And then hydrogen sulfide everywhere. So when you smell hydrogen sulfide, run away because your sensor, which is your nose, still working. By the time it doesn't work, basically you die, right? Anyway, okay, that's a safety. I hope somebody teach you this because when I work in a refinery, all those the safety the people they tell me, hey, you smell something, low concentration ammonia, run away. Low concentration hydrogen sulfide, run away. That's all. Don't try to solve the problem. I don't know in India, is it everybody's the responsibility to find the reverse leaks? I mean in the U.S. refinery, there are some safety people. You run away and you, in a safe location, you tell people, hey, that place has a hydrogen sulfide, that place has ammonia. Don't try to solve the problem because if you try to solve the problem and then you die because you never know where the source is. Okay, that's for safety. All right. So this is the last part of today, which is very interesting. So I cannot basically I'm going to talk about the hydrogen production via the microwave induced water splitting at a low temperature. So you can split the water different way, and then so this is really the using microwave splitting water. So what before we go ahead. Anybody has any question? Go ahead.
Yes, sir. Sir, it's any chemical or neutral agent to neutralize the hydrogen sulfide in oil or a gas or something like that? Is any agent or the chemical agents?
Yeah. So yeah, you still talk about so hydrogen sulfide. If you drive in a refinery, you can smell it, especially during the raining day, because hydrogen sulfide in the gas during the raining day, they will never leave, and you can smell. It's more like what you call that? It's more like if you have egg, right? If you eat egg like stay there for a long time, it's just like it's a hydrogen sulfide. I mean, a little bit of hydrogen sulfide is fine. You can smell it. Don't get closer. That's my point. If you get closer, it's the effect is worse than ammonia, because it's just you basically lost the conscious, because the low level, your nose, which is sensor, still working. High concentration, it's too late. Yeah, ammonia, same thing. 37% ammonia in the bottle, open it, doesn't kill you, because they go to the air and then dilute it. But if you have 100% ammonia tank leaks, be careful, because that ammonia come out, and then if the alarm doesn't sound, that's dangerous. So if you smell a little bit, any of ammonia, if you smell, just run away and then call somebody, because whatever the safety people, they need to wear the so-called the mask, right? So those kind of the filtered mask, they can solve the problem, but not you. Without protection, just run away. Okay. So I think someone has a question about hydrogen sulfide. Yeah, hydrogen sulfide also in chemical refining is everywhere, because it's a sulfur, all right? So if you have especially if you use coal or some high sulfur content natural gas as the fuel, and then you burn them, hydrogen sulfide sulfur supposed turn into the SOx, SO2, SO3, but that never happened, because because some of the incomplete combustion, and then they will release some kind of hydrogen sulfide. Yeah. So and also SO2, SO3 is a different poison, because when they get in the air and then react with the water, so you have sulfuric acid come out, so-called acid rain. That's very bad as well. So, but the hydrogen sulfide and ammonia, they are different animals. Okay, SOx and NOx, people know already, but hydrogen sulfide and ammonia, people didn't pay attention to it, because they don't have knowledge on this. Okay. Yeah. So let's talk about last part of this section, because next session we are going. Oh my God, time flies. So anybody any question? Go ahead.
Yesterday's session you said we can generate hydrogen from shale rocks from underground by microwave. Thus, the microwave will be transmitted long depths inside the depths without any losses.
Okay, let me go back. Good question. So this is water slipping microwave. Okay, I can save this for the next session, but let's go back to underground. Okay, very good question. Hold on. So you are talking about yesterday, is that right? Let me see.
Sir.
And yeah, so let me go open that cartoon. Then I want to understand your question. Hold on, give me 1 second. Okay. Where's my slides? I need to go by my slides yesterday. Give me a second. Okay, I found it, and then I'm gonna share with you, so you can tell me your question. Okay, I'm sharing with you. Okay, so this is your question. Go ahead. What's your question on this one? And basically, this yesterday we talked about a lot of hydrogen. So methane pyrolysis. Now you can do methane pyrolysis underground and leaving carbon behind. If you are only interested in hydrogen, this is the way to go. You can leave carbon behind. So this carbon and still the support underground structure. So that means the underground structure shell will not collapse because you still have carbon majority and holding the structure and hydrogen come out. So what is the question? Could you repeat the question? Please speak very slowly. Go ahead.
Can we transmit via microwaves for long distance underground without transmission losses?
Thank you. That's a different technology. Okay. Did you see this cable on the yeah. So basically, you can drill. So the reason, you can. The answer is yes. You can put a microwave in that long distance. Remember, how you generate microwave. You have a generator, is that right? So you have a generator, and then when you drill this, you don't have to put a generator in there. You can put what you call that, either called antenna or something, whatever can carry the energy of microwave, drilling along the drilling cable and then put into underground. So that's why I draw the cartoon here. All of this. I'm going to show you. Very good question. You should ask me yesterday. So it's a very good question. I'm gonna look at this circle. I'm going to interpret to you. Okay. This is the rest of the circles. So it's a one segment, another segment. Okay. So it's called a coaxial transmission line. I don't know if you understand coaxial transmission line. So when you drill, this is different. It's engineer. When you drill into the shell, so you basically you have a cable, and then the transmission line. Transmission line basically there's coaxial feature. You drill and put it in, and then you can basically have a microwave transmitted through this coaxial line, and then the microwave can be transmitted into this section. That technology already in place. Did I answer your question?
Another question, sir. Can we trap all hydrogen produced underground, sir? Fully we can trap, or we can only partially trap the hydrogen produced?
Only partially hydrogen produced. So in here is a microwave pyrolysis. So when you have a microwave come in, microwave will basically drive the methane decomposition, and then the hydrogen come out. So I couldn't understand your question. You say the partially?
Can we trap the hydrogen 100%, or we can?
Okay. Now you don't have okay. I know your question. Okay, so let's say see this is the orange the color here. Actually, your question is economical question. It's not technical question. I thought you have technical question. Technically, I answer you. You can transmit microwave into the underground. So let's say that you have a 100 pound of methane in there. Okay. So your question is, can you convert all of them into H2? Is that right? Is that what your question?
Yes, sir.
No, you don't have to. Economic, why don't, I'm not joking. Don't be so greedy. The natural gas in here is free. I'm talking about shale gas, all right? So shale gas is free, and then if you convert 80 tons of them, you win the game already. So to answer your question, technically, yes, you can. If you place all of the different segments all over place around the border of this 100 ton of the ammonia location, because ammonia, no, I'm sorry, not ammonia, natural gas, methane in here is basically buried in the shell. If you put in theory, if you put all this microwave around it, yeah, you can drive 100%. You don't have to, because they're so cheap. As long as you have the microwave cover enough region, and then in this, if you convert a 60 ton of methane, you win the game. Your question is economic, so you don't have to. But in theory, yes, you could. But you have to have all this the ammonia, so coaxial the cable all over around. That's too much the money on the equipment side. So I hope I answered your question. Yeah, this is economical question. Yeah.
So does this have any changes in seismic activities? Get crushed?
You mean the challenge of what? The pressure?
Yes, sir. When the pressure increases, the minor earthquakes can come. Seismic activities will be.
So the
possibilities.
Yeah. So the pressure does affect the methane pyrolysis because I think we are running out of time. Can we talk about this? I don't give you guys the 30 minutes the break. We'll come back. I will leave this on my screen. When you come back, we'll talk about it. Good question. Yes, pressure affects the ammonia pyrolysis. I will show the equation. Yeah, very good question. So should we take the 30 minutes the break and then we come back?
Sure, sir. Sure, sir.
Okay.
We will meet after.
Yeah. So we will take 30 minutes break. All right. Then we will resume. Come back. That'll be last session for for today, and also last session for the whole course. Very good question. I want to keep this in here. Pressure technical does affect the ammonia. No, I keep on saying ammonia. Methane decomposition. Yeah. Okay.
Thank you.
All right.
Yeah.
Thank you.
Thank you. We'll meet after 30 minutes.
Okay. Yep.